Thank you, Rachel, for the very ominous introduction. No nerves at all. So welcome back. It is really, really amazing. The last time we did NCM, there was a guy called Pete and a camera, and we looked at him and we smiled. But it's really, really great to see so many people in the room. It's amazing to hear of the enormous audience that is out there listening to this now. And we hope to keep it high tempo, energetic, because we know that in certain parts of the world, it might be some people's bedtime. So this is our update, for our tech update. We've got a lot of things to pack in. I'm going to talk about where we are now. Stu's going to talk about where we're going next. And Lakmal is going to give you some breadcrumbs into where we may be going in the future. A quick statement, we will be making forward-looking statements. This is an R&D tech update. And of course, we are giving you projections of where we believe we'll be going. So let's begin. Well, actually, you know, NCM is always a really great time because there are some holidays coming up, and anyone who would like to see the full history of Nanopore tech updates, you've got some days coming up. We hope you can enjoy them, but every single talk ever that Nanopore have done is recorded, it's online, and available to view. Let's talk about our technology. Our vision is to take this technology and enable anyone to sequence anything, anywhere. And you, the community, have taken this technology to all different parts of this world. You've taken it at the greatest speed, and you've taken it at the greatest, you've made it work at the greatest volume. At the center of everything is a nanopore. As all of you know, we have different types of nanopores, R9s, R10s. We have an enzyme that controls the speed at which the DNA gets fed through the nanopore, and of course we've got different run conditions, software, etc., that feeds this DNA through and controls the speed. It's the reading of native DNA that gives Nanopore all of its unique qualities. And we've really enjoyed all of the talks that we've heard today, that where we can really see the community tapping into this capability. Because you get the full biology, you get the SNPs, you get the indels, you get the methylation, structural variation, phasing. Some of the talks today around phasing have been really, really exciting. And of course, assembly with the T2T assembly that we started at the start of today. We can read any read length, so from 20 bases to over 4 million bases, and we can scale it, anything from a flongol all the way up to a P48. These come with Nanopore unique features, simple workflows, accessible, CapEx-free, real-time analysis, upgrades included. And these are things that we really stick to in the principles when we develop and launch our products. So look into 2023, where do we want to go? We're building off a really solid chemistry foundation into 2023. We've now had the R10 series in early access for a number of months. We've had Kit 14 in early access for a number of months. And we now have R10 available on flongol, on MinION, on PromethION, and you will very, very soon see in the store that we will move all of our 10 nanopores onto the typical flow cell warranty period that you get for R9. On the Kit 14 side, we have the ligation and the native barcoding chemistries out. Those are our most popular chemistry types. And of course, the rapid and the ultralongs will be following very, very soon, leaving us with rapid PCR and cDNA to do in the new year. So we are continuing with that promise that we will continue to support our users who are on R9 chemistry until the end of next year. So we've had our developer release of R10.4.1, we've had our developer release of Kit 14, we've had our early access. We are now focused on getting R10.4.1 and Kit 14 into the released phase. We've discontinued Kit 12, R10.4, and we will be making moves into the R9 transition. So transitioning all of our users' projects from R9 into R10, it's a big job. And many of you will be getting emails, or will have had emails last week, offering MinION trial packs so that you can start to understand what this technology can do for you. There are also better things that we could be doing with our digital platforms to support all of this transition. So store upgrades, so available now, you'll start to see a legacy tab where all of the old chemistries will be available for you to request. This really simplifies the store. We've spent a year where you've got kit 9, kit 10, kit 11, kit 12, kit 14, all of these things on the same user interface. And what we're doing is pushing all of this into the legacy tab, so you have a really clear picture of where we're going. Our digital team are working on My Account upgrades so that you can upgrade your own order next year. So if you have our 9 flow cells on order, you can simply change these over to our 10-for-1. And we will also be releasing a compatibility checker so that people can check what kits work with what and flow cells in different versions. So hopefully these digital tools are going to support all of you in this big transition. We're doing all of this because we really have and enjoy having a simple but very, very robust product offering. So we have the prepare, sequence, analyze. On the preparation side, we've got simple manual library preparation kits, automation solutions, and of course adaptive sampling, a unique feature to Oxford Nanopore. So during next year, what you will see is that we are, of course, upgrading our entire library preparation range over to kit 14. We're going to be really focusing on our ligation kit, bringing a lot of the capabilities that we currently serve with different kits, such as direct cDNA or Cas9, bringing a lot of those into the ligation kit because we really feel that we can further optimize the ligation kit, despite the fact that it's already a very streamlined 60-minute workflow. On the automation side, Kit 14 workflows are already available on automation platforms. We continue to expand the menu of automation, both the companies that we're working with, but also the preps that we're automating. And we're working with Hamilton, TCAN, Beckman Coulter, OpenTrons, Agilent, Eppendorf. And we've created an ecosystem where either we're developing protocols, the vendors are developing protocols, our users are developing protocols, and they're publishing them on our community, and they're available. So please do look. We have an automation page, and you can register your interest and get support from the team. We're also making initial inroads into automating and bringing platforms like the MinION and the P2 into a fully integrated liquid handling solution. And I will talk a little bit more about this tomorrow. So this is our large liquid handling product offering. Of course, we've got VolTRAX that is in early access. It's been actually quite a busy year for VolTRAX this year. We've launched our PCR capabilities, the blue cartridges that enabled all of that. That then followed with a sequencing kit, a COVID kit. We then genericized that COVID kit to an RT-PCR kit. We've had successful runs with things like tuberculosis. There was a really great talk earlier today about TB, and our VolTRAX teams have shown you can do TB using this methodology, but also Mpox. In our pipeline, we've got multiplex kits, direct RNA, ligation sequencing kits. So again, if you're interested, please register, and also speak to our VolTRAX team who are out there to answer any questions. So we're going to move from sample prep to analyze. And anyone who saw Stephen Rudd do a nice presentation, I'm not as energetic as he is. We get actually constant requests from the company for Stephen to do all employee meetings to really get everyone buzzing about bioinformatics. But this is something that some of you may have seen before. This is our current ecosystem. We've had this for a while. So we've got Epitome. It's a cloud-based, real-time, pre-configured workflows. Really, really easy to use. I can use them. You can go in and you can do metagenomic analysis, for example. Our labs teams have been creating local and distributed workflows, so things that run on laptops, on sequencing devices, on clusters. Again, sort of post-run, real-time, configurable. And of course, you, the community, have been publishing all of your great work on GitHub. And so to give a flavor of what we've been doing is we've been taking all the great work that the community's been doing, pairing that up with the labs team, the Epitome team, and making really easy to use workflows for infectious disease, biopharma QC, the all-human variation workflow. It's really, really exciting. So you can get the SNVs, structural variations, modifications, copy number variations. You kind of know that you're done when you're sort of leading bioinformatics expert from the apps team says he just uses Epitome. You know you're doing a really, really good job there. And of course, the team have automated the single cell pipelines as well. So the question is, how do we take our current ecosystem where you've got cloud-based informatics, you've got on-demand informatics, and you've got everything that you guys do in GitHub. How do you take those ecosystems and bring them together? And the answer really starts here. So the Epitome team have developed a method where anyone can import a workflow. Of course, there are standards that you need to follow, but you've now got an import workflow button that you simply click, and you can start running your workflows, your pipelines, analysis pipelines inside Epitome. There's a registration of interest for this. We really, really want to understand how you want to use this capability and take it forward. So back to our sequencing range. There are 4 things that we try to do every time we develop and launch sequencing products. These are our 4 core values. We want to make our product accessible, capital-free. Our pricing is transparent. Our upgrades are included. And we work very, very strongly with our community. We have these meetings. We talk to you about where we want to take the technology, what are the new products, the new ideas that we have in R&D. So we want to listen to what you think you want to do with that and take that into our development process. So around our sequences, around that capital-free, we have this model, the starter pack model, for anything from a Flongle all the way up to a P48. And all of these, they're starter packs, and they include all of the reagents, all the consumables that you need to do a significant amount of sequencing. And that's really because we believe that, your research money is better spent sequencing than investing in big hardware. So, of course, that is our model, and that is what we really stick to. On our price per gig and our transparent pricing, our flow cell pricing is available to anyone online. And as our outputs increase, the price per gig decreases. Many of you here are early mappers. I've seen many familiar faces that I haven't seen for many years, and it's great to see you. And you will have been on this journey where MinION started at 300, 400 megabases, and we now have users achieving as much as 50 gigs. And so it kind of starts posing the question, where can we take this platform? How much further? We have a lot of headroom in our platform. And the key things that really drive output are enzyme speeds, run conditions, pore blocking. All of these are really active areas of research for Oxford Nanopore. And so if we take PromethION, for example, and right now, we have a lot of users generating a genome per flow cell. It takes us from 200 genomes on a P2 per year all the way to 5,000 genomes on a P48. As we get more and more outputs, you're going from 400 to 5,000. And in the future, if we manage to get up into the realms of 300 and 400 gigabases per PromethION flow cell, we could be having a P48, a device that is out there now, generating up to 20,000 genomes per year. And all of these, again, with prices that come down and become incredibly, incredibly competitive. But back, from the what if to the what now. So right now we have a platform where every single part of our platform is exposed to users. So anyone who wants to go on the ultra long, anyone who wants to multiplex, anyone who wants to go short read mode, all of these features and all of these capabilities are completely open. And it enables you to generate the new biology that you're generating, that we hear about at all of these conferences, and is really exciting. As we've been going through into production sequencing, what we've figured out with the help of all of our production sequencing partners is that production sequencing actually needs a really, really consistent workflow. And if we apply a very consistent workflow, when we run the same sample, the same extraction methods, same library prep, same reloading methods, you can see that actually our production accounts, if they set a target, for example, of 90 gigs, more than 90% of their flow cells are reaching that. And with the launch of P2, there are so many new PromethION users coming into this space. So what we've done is we've wrapped up all of the lessons from our production sequencing accounts, and we've published a couple of workflows now for people wanting average read N50s of 10 KB. There aren't many of those. Most want longer. And we've also published a 30 KB N50. We've paired this with the simple end-to-end workflow from Epitome. And really, if users are running this, our expectation is that they should be seeing about 100 gigs. And we have and are investing very, very heavily in a support team and an expanding FAS team to enable to get you there. Now, there's something that, as our FAS team have been out talking to users, working with everyone, There's a little trick that we have at Nanopore that we realized that we hadn't actually translated into the field. So here it is. We spend all of our time thinking about how to maximize data per flow cell. That's what a lot of our users say. They want to get the best price per genome, best price for a flow cell. But there are actually a really significant number, an important number of projects where you have incredibly precious samples. You've got biopsies, rare species biobanks, and there actually it's all about the maximum data per sample. So something that we've kind of known about, but again, we've been so busy doing the maximum per flow cell, is you can actually load a flow cell, you can run it a number of hours, you can run it for the full length of the flow cell. And when you stop that run, you can take the library and you can load another flow cell and you can run it again. So this really will help users who, if for whatever reason they haven't quite managed to get the output that they wanted, they can simply retract that library, place it on another flow cell, and run it again. And we're working now with groups who've got incredibly precious samples, and we will be making this protocol public during December. So a look back at 2022. We've been busy. Our team actually just counted 98 release notes up on the community. Key themes around them, of course, Remora methylation, Q20, short fragment mode, single cell, the PromethION A100 towers, PromethION upgrades, Dorado, Pod 5, and high Duplex for developers over the last week. And we've really also had an amazing time getting the PromethION, the P2 Solo out. It's been the kind of feedback that we get, it kind of feels a little bit like it's a new MinION again. And we're really, really excited to expand our user base for PromethION. So we will continue to focus on our PromethION next year, but we will also be coming back to where it all began with the MinION Mk1D. So we're updating our MinION, USB-C, much better temperature control, getting all of the Q20 temperatures that we need. And more importantly, this device is going to interface beautifully with an iPad. And this is going to lead us to the next generation of portable sequencer. So we're going to be pairing the amazing compute capacity with the new M chips, 5G mobile connectivity, we've got improved thermal performance through the MinION, but also an industry-leading user interface. My mother is going to be able to sequence on Nanopore. She'll probably interrupt my FaceTime calls with her, but that's okay. And so with that, here are our target release times. So we've got, of course, the P2 Solo is now fully available through early access. The P2 developer will start in March next year. We've had high Duplex out, a lot of VolTRAX activity, a lot of sequencing kit activity. But now for all of the more detailed information on exactly what we're going to be doing, I'm going to hand over to Stu Reid, who's going to talk to you about our development and what's coming next. Thank you.
Okay. Thanks very much, Rosemary. And just to reiterate the comments, it's great to be here in New York. It's great to have so many people here physically, and it's great to have the audience online too. So I'm going to give some technical updates of, I will cover a little bit of where we are now and where we're going in the immediate future. And I'm going to dive straight in with the headline number slide. And the purpose of this slide, at this conference already, there's been loads of talks, absolutely stuffed full of applications from you, the community, for our own applications teams, loads of posters out there. So a lot of you know what to do with this data already, but I would encourage you to look at these numbers and extrapolate from there. What can you do with these sorts of accuracies? What does accuracy mean for you and for your application? So we're at raw read accuracies, 99.35%, Q22, that's a new run condition. I'll talk about that in just a minute. Duplex accuracies greater than 99.9, Q30. SNPs, 99.9%. Indels, if you restrict to those coding regions, 99.5%. Assemblies, highly contiguous diploid assemblies, combined with pore C, you can fully phase those. Phil showed a bit of that earlier today. Bacterial assemblies, circular, greater than Q50 is sort of where our QC measurements top out on that one. Those are on one of the app's posters. It's one of the digital ones, so it's not up out there, but it's on the iPads out there. So do take a look at that. SV detection, 96%, that's where the ground truth basically is. We think we need to improve the ground truth to do better there. Methylation accuracy, 5MC raw read accuracy, 99.5%, actually better than the base calling accuracy. So pretty good methylation. So with those sorts of accuracy figures, you can develop highly sensitive, highly specific tests. And we did that ourselves a few years ago now with Nanopore COVID test. Various other tests can be done. You can generate a lot of data with Nanopore platforms. Our instrument record, we've had this for a while now, 10 terabases on a P48. Our flow cell records, 350 gigabases now. That is a new chemistry. I won't steal too much of Lakmal's thunder there. But in the field, with the existing chemistry, we've seen 245 gigabases. We appreciate that not all applications deliver those sorts of numbers consistently, but as Rosemary said, we think for controlled workflows, 100 gigabases is a good, realistic, reproducible target. Short fragments, we've demonstrated before over 250 million reads of around 200 bases. That's consistent with the sorts of things you get from cell-free DNA. And of course, Nanopore, we are well known for read lengths, long reads. Our internal record is 4.2 megabases. The one we have in the bank from the field is 2.3 megabases. I think that might have been beaten, actually. So please do get in touch if it was you that beat that. I apologize. And with our duplex chemistry, previous duplex chemistry, this is actually the longest Q40 read we've seen. Q40 being a benchmark that is talked about as the sorts of accuracy you should aspire to. Our longest Q40 read is 143 kilobases. Okay, so this is where we are now. These numbers have actually come from slightly updated models, but they're consistent with the accuracies you have in field now with our 400 base per second kit 14 condition. I'm going to focus exclusively on the 400 base per second condition. So you can achieve greater than Q20 raw read accuracy with our super accuracy base calling models. As Rosemary said, we intend to move on the basis of these sorts of accuracies, these sorts of outputs you can get for various most of these are human applications, human output numbers. We expect to be able to move this in Q1 from early access to a released status. So this is the base of our technology going forwards. And as I say, we expect those established workflows where you control the samples and you control the protocols to routinely exceed 100 gigabases on a PromethION flow cell. And we will help you get to that point. Okay, so with those sorts of raw data, the raw data adds up to consensus. You can do variant calling over depth, things like that. You get complete, contiguous, accurate genomes with Nanopore data alone. I mentioned those Q50 bacterial assemblies with very modest coverage, and you get a comprehensive picture of human variation at the push of a button. This is the Epitome Labs workflow up there. SNPs, indels, structural variants, and methylation. I'll talk about methylation in a few slides time. And you don't need to go up to those 60x depth numbers. They're numbers we quote, but you can get very respectable results all the way down to 20x. So you can, today, multiplex human genomes on a flow cell should you desire and should your application be suitable for that. Okay, so we have a run condition update coming, and this builds on a huge amount of engineering work behind the scenes from the teams. And we heard Alex Murray spoke about this actually this morning in the Data for Breakfast session. This builds on the MinOPod 5 raw data format. And getting that raw data down onto disk has been somewhat of a bottleneck for us. And now we have opened that bottleneck a bit wider. We can up the sample rate from 4 kilohertz, which you have now, up to 5 kilohertz. So we're measuring current 5,000 times a second per nanopore. You combine that with the latest updates in the base calling models, and we're giving high accuracy base calling now. So this isn't our most expensive model. This is high accuracy base calling. This is now at Q20, and that model will deliver keep up base calling performance on a PromethION A100 tower when we get Dorado integrated, and that will be early next year. The SUP model is now at Q22 for 400 bases per second. We think that covers most of the application space that people were using the 260 base per second condition for, and we are on a drive to simplify our product offering. So we are going to deprecate that 260 base per second condition, so you no longer need to make that choice. If you do have ongoing projects, please do get in touch. We can offer continuity support, but I think we've got most of it covered with 400 bases per second now. So I mentioned there are a few sort of various bits and pieces there in the models as well that come coupled to this new condition. We will be releasing, so we have released standalone V4 models for the 4 kilohertz condition as well, so you can get those now with Dorado. And one of the things that those models deliver us, as well as a slightly tweaked performance across the board, is we are seeing really compelling performance in the telomere regions now. And that's the best I've seen from any sequencing technology in telomeres. And those stripes down there, we're pretty confident that's real variation. So do try out those new models, recalling your existing data. Okay, on to base modifications. And Marcus gave a jam-packed talk this morning in that Data for Breakfast session. That will be, if it's not already available, that will be available on demand tomorrow, so you can catch up with that. With nanopore sequencing, I think Rosemary touched on this a bit. You've got a piece of DNA in a nanopore, and we say we are directly reading that. And what do we mean by direct? So that piece of DNA sitting in that nanopore is being bombarded by thousands of ions, thousands of times a second, and we're measuring that current that's flowing through that nanopore. And each one of those ions going past is taking some sort of read of the interaction, the chemistry between the nanopore and the DNA. And because we're doing that sort of direct read, and we're reading that complex chemistry, there's no real reason why a modified base would be any less different from its canonical partner than the canonical bases are from each other. And that's basically what we see in the signal. Just because it's called 5-methyl-C doesn't make it any more like C than any other bases. And we get really, really accurate raw read methylation calling there. And I think Marcus had a question this morning, which is what depth of coverage do you need to do accurate modified base calling? His answer, 1x. It's as good as our base calls, 99.5%. So you have a Kit 14 model for 5MC calling. That's available. That's integrated in MinION. In Q1, we'll be releasing the 5MC and the 5HMC models integrated with MinION. They come coupled with the new base calling models, although they are available standalone now if you want to recall data that you have. So that's coming shortly. Okay, duplex sequencing. So duplex sequencing is where the second strand follows the first strand through the nanopore. And you get 2 orthogonal signals. Catherine spoke about this morning again in the data session. Catch up with that tomorrow too. 2 orthogonal signals provide complementary information, and that gives you a very accurate duplex base call when you combine those signals. We have a new duplex base caller called Stereo. I'll come on to that in just a minute. Of course, the trick with duplex is to get the second strand to follow the first strand through the nanopore. And we have a developer release ongoing right now of high duplex flow cells. And with that release, you can expect the majority of data now in duplex pairs. We see up to 70 or higher with an idealized sample PCR E. coli. There is no additional library prep required. but you do need to ensure that you get good ligation adapters on both ends. And if there's any damage in the sample, of course, that will impact your duplex rate. And we think some of that at least explains the difference between the native human and the PCR E. coli numbers there. So improved duplex rate in the field now. And what sort of accuracies do we get? Well, Q30 or higher. We're certainly aiming for higher than Q30. The new stereo base caller I mentioned, that actually delivers those base calls in a similar runtime to the Simplex base calling. So if you've used duplex base calling in recent history, you found it a little bit slow, we've fixed that. It's about the same runtime as the Simplex base calls. Catherine showed this morning, and we've shown previously, that duplex accuracies are independent of read length, so you can get those long nanopore reads with duplex levels of accuracy. As I say, we do have a duplex developer release ongoing, and we're hoping to see similar results to those that we've presented from the field. What you see with duplex, we've got the progression of our chemistries here. IGV screenshot. You've got the R9 kit 10 going to the R10 kit 14. I think that's a pretty compelling reason to upgrade from R9 if you haven't already. But then when you go to duplex, you see a clear improvement again. And we're showing about 5 kilobases here. And I can count on one hand the number of errors per read in those duplex base calls. Really compelling, visible accuracy improvements if you go up to duplex. Okay, on to Dorado. So those of you who are avid Nanopore followers will know about Dorado. Rosemary mentioned it as well. This is a new base caller, about a year old now. Dorado is now mature enough to become the recommended solution today for offline base calling and modification calling. And we expect to see those performance benefits that we've got with Dorado integrated into MinION in Q1. We've got the performance benchmarks here, and a reasonable definition of keep-up base calling on a P24 is maybe 200 gigabases over 72 hours, 3 days. That's probably keep up in most circumstances. And that's, again, huge engineering effort from the team. If you want to see those sorts of performance improvements with offline base calling, you do need to be coming from our Pod 5 file format. It's dependent on that. You can't get these sorts of performance figures over the old Fast5 format. Okay, so features we've got coming soon. Barcode demultiplexing and alignment. We need to get those done, and adaptive sampling before we can replace Guppy and Minnow, so that's why it's going to take us a few months. But we have recently added a duplex pipeline and Apple Silicon support M1, M2 there for base calling. As I say, catch up with Mike's talk if you want more details there. Okay, so Nanopore is a real-time sequencing technology. And because you are reading that DNA as it's going through the Nanopore, you can do things like run until. Now, this feature has been available to you since the start of Nanopore sequencing, but you've had to sit there and watch and press the button yourself. We have now got that finally integrated into Minnow. This will be coming out in Q1 next year too. Lots happening in Q1. So Minnow monitors are run, so you don't have to. So the way we've done that is a gigabase target. So you can stop the run when you've generated as much data as you wanted to generate, and you can save the lifetime of that flow cell for the next sample. So that can reduce your cost per sample. And we do see quite a lot of flow cell reuse in the community already. So this will help you with that. Another key feature when you're doing real-time sequencing is adaptive sampling. And we have spoken about this several times before, but in brief, it's where you sequence the first part of a piece of DNA going through your nanopore. You decide if you want to keep sequencing that piece, and if you don't, you can kick it out and you can grab a new one. And that way you can focus your sequencing power on the regions where you want to measure. Our typical application is a cancer gene panel with about 200 target regions, and we're seeing a 4 to 5-fold improvement over the control here. And the new thing here, we've shown similar things on GridION before. The new thing here is we've got this running on P2. So you can now get those sorts of high-depth human genome sequencing panels. And you can spend that depth how you want to. So if you want to go deep and measure something rare in a sample, you can now get, we've shown 175, you can probably go further than that. Or you can multiplex different samples on that one flow cell and reduce your cost per test. So various options there with adaptive sampling. So here's the timeline that Rosemary showed. Hopefully I've filled in most of those boxes that she didn't talk about. This is what you can judge us on by the time we get to London Calling. There's a lot happening the first half of next year. That's as far as I see, that's as far as Rosemary sees. Lakmal can see a little bit further than that, and he will tell you about some of the things going on in research. So I'll hand you over to Lakmal.
So thank you, Stu. So as he said, so I'm going to talk to you about in this section what we are currently developing in R&D to give you a glimpse into the future. So, so this is one of my favorite slides. In a nutshell, this summarizes what we do in R&D to improve the properties, the performance of our platform and chemistry. So as you know, like this is a multi-component system. So we have biological nanopores, we have motor proteins, and we engineer them, and we make like hundreds and thousands of mutations of these molecules. And then we have different run conditions. We have membranes, electronics, hardware, which constitute the platform. So we improve all these components to improve the signal to noise, and then software and informatics play a huge role to decode the signal into the sequence that we want to know. So when we are talking about engineering biological molecules, the enzyme and the motor protein, up until very recently, we've been using traditional protein engineering methods. But recently, we have started using machine learning approaches to engineer our motor proteins and nanopores. So our machine learning team uses protein language models, 3D structure models, and hybrid versions of those two. And doing these things in combination with high throughput protein sequencing or protein purification methods that we have developed in-house, we can now design, purify, and scan hundreds of these new molecules in a very short time. So in this particular example, I'm showing what our machine learning team has done in combination with our enzyme engineering team to develop new enzymes to increase the speed of our system. So the x-axis of the graph on the left is relative speed, y-axis is the relative accuracy. So we choose a particular enzyme, and we wanted to see what we can do with machine learning to improve the speed of this particular enzyme. So the cross-section of the dotted line is where the control enzyme lies, and then each dot of these plot is a new enzyme version that our machine learning team designed, and then we purified and screened. So each of these molecules, each of these dots is representing the speed and the accuracy improvement of new molecules relative to the control enzyme that we selected. So as you can see, so there are quite a lot of hits with improved accuracy and improved speed. So we have selected some of these enzyme molecules, and then we combine these effects, and so we end up with some enzyme molecules that we can now use at very high speed to achieve high output. As you can see in the plot on the right, so there are some enzyme molecules are now hitting 1,000 bases per second speed. Our current system is 400 bases per second, so this is a real improvement. And accuracy of these enzymes are actually not at Q28, so we are working on conditions to improve the accuracy as well. But with these enzymes, we can now hit reasonable output. So Rosemary talked about what if we can hit 400 GB in a single flow cell so that we can do multiple genomes in a single flow cell. So we are already hitting about 350 GB in a single PromethION flow cell with some of these enzymes. So our teams are working very hard to improve the accuracy of this system, and these molecules are Duplex compatible as well. So when we have matching accuracy to complement the high speed, those flow cells will be a real big improvement to our system. So home polymer accuracy is one of the key features that we always want to improve. So we moved from R9 nanopore to R10 to now 10.4.1. So in R9 nanopore, we have a single reader head. In R10 nanopore, we have 2 reader heads. And, but we are still having some errors because of the homopolymer issues. So to sort out homopolymers for good, we need to improve read head length even further. So we have now, we are developing a new version of nanopores with much longer read head. In R10 series, the distance between the 2 read heads is about 5 nucleotides. So in this new nanopores that we are developing, the distance is like almost double, so that will have a significant impact. When we talked about this pose in last year in NCM, so single molecule accuracy was actually quite low, but now we have improved simplex accuracy significantly to about 98.5%. Still, there's little more to go. And so as you can see in the plot bottom right, so in R9, so you can see poly T sections are quite flat. In R10, there are subtle variations, but with this longer read head, the variations are even more. So which means it breaks the flatness of the poly T region. So there are steps, which means there are information. So we are using this information to improve the homopolymer accuracy. So yeah, so the modifications. So Stu talked about modifications, and Marcus talked about modification in the morning. So everything Stu talked about, modifications, 5MC, so models for those ones were built on just like GC context. But we obviously want to build models that can call modifications in all contexts. So the GC context models were generally built using training data sets. They were generated enzymatically, but it's very difficult to generate full context data sets enzymatically. So we are now developing a new method to generate larger data sets to call modifications in all contexts. So this is the randomers that we are talking about. So in randomers, so in this particular example, so the middle section is, the gray section is the randomer in all contexts. So it's about like 60 nucleotides long, and in the middle of that, we have a specific modification. Spanning that randomer region, there are fixed sequence, and then we fill in the complement strand, so we can then duplex base call and get the reference sequence of these randomers. So we are using these randomers now to develop new base callers for modifications. So we have developed 5MC all context modification, all context base caller. And with that, we have accuracy of about 97.72 in CG context, but in random context, in all contexts, we are hitting 97.45%. So in the graph on the bottom right, you can see that in Remora, in our current CG context model, accuracy is about Q25, and with the randomer models, accuracy is slightly lower. There is still a gap to fill. And we are closing this gap by improving the training sets, making training sets larger. So in this particular example, the 5MC model, randomer model, was made with about 2 million strands, and we are going towards 20 million strands to close this gap so that we can have a randomer in all context model closer to the CG context model as well. Not only with 5MC, so we are developing randomer models for other modifications as well. So we are developing 6MA models and more exotic 8-oxo-G model and ribo-C model as well. So in the graph on the top right is the very kind of early version of the model for 6MA. And the top part is the modified reads in this IGV visualization plot. Bottom half is the control reads. So as you can see in the modified reads, all the modifications can be called accurately, but there are some false positive in the control section as well. So our modification team is working very hard to improve these models with better data sets so that we can call these 6MA modifications very accurately. So in the bottom section is an even earlier model for 8-oxo-G. So the black line is the unmodified signal, and the red line is the modified signal. In the orange sections are the 8-oxo-G modification is. So if you look closely, you will see that in the red line where the modification is, the signal is actually quite disrupted, which means all the information is there. So our team, again, is working hard to extract all this information and to develop this 8-oxo-G model. So when we develop these models, it will be really nice to see not only 5MC, 5HMC, but with other modifications as well. So as Stu said, Marcus talked about these things in detail in the morning, and that talk will be available from tomorrow on demand. So switching gears a little bit, I want to talk a little bit more about Outy sequencing. This is like finding a needle. In the morning section, our application team talked about finding a needle in a haystack as well, but this is actually finding even a smaller needle in a bigger haystack, I would say. So in Outy sequencing, we talked about this in London Calling last year. So it's a quite nice method. So in our INI sequencing that you guys are using at the moment, or we talked about so far, we push the DNA through the pore while sequencing. So in Outy sequencing is the other way around. We first capture the DNA from the 3' end, and then we pull it through the pore, and then the DNA will be, the enzyme motor will be pushed towards the other end. And at that point, when it is towards closer to the other end, we pull the DNA again and sequence while pulling it out. So there are a few interesting features of Outy sequencing. The first thing is that we can do size selection. So when we push the DNA in without sequencing, we can get an idea about how long the DNA is. If it is short, you can just eject it without sequencing. If it is long enough, you can then pull it out and sequence. So which means you can really do size selection before doing sequencing. So the second interesting feature of Outy sequencing is adaptive sampling and rereading. So when the first strand, so you push it through the pore and then you pull it out and sequence, and if it is interesting molecule that you want to sequence further, so you can feed it back into the pore and sequence again. So you can do it multiple times as long as you want until you get the right accuracy or you get the right confidence. So this is adaptive sampling, reread until, and so the accuracy will be higher because you can read the same molecule multiple times without letting it go. So when you are happy that you kind of sequence it enough, so you can then eject the DNA strand and capture the next molecule. So Outy sequencing has improved significantly over the last year. So again, by the time we talked about this in December last year, Simplex accuracy was less than 95%. So we worked hard on this Outy sequencing method. So we developed new pores for Outy sequencing, and there's a specific motor for Outy sequencing. And now Simplex accuracy is about 98.5%. So it's still improving. And on the graph on right, so you can see the depth of sequencing versus the accuracy. So if you reread multiple times, accuracy improves significantly. So in this particular example, if you read 12 times, reread 12 times, accuracy is hitting Q37, Q38. So this is a really nice way to go towards Q40 accuracy sequencing. So this is so the same platform, and you can do short DNA to long DNA using Outy and hitting these high accuracies. So another very important aspect of Outy sequencing is, this is actually what I'm talking about a needle in a haystack. So this is a very important slide. So in this particular example, what we are showing is that you can dilute a very rare variant into the wild type. So in this particular example, we took a DNA fragment which contains 5 different mutations and mixed that with its wild type counterpart in different dilutions. So we diluted the variant 1 in 10, 1 in 100, and 1 in 1,000. So on the left-hand side, you can see the pileup of individual molecule rereads. So in the middle plot, what you can see is the detection frequency versus spike in frequency. In all cases, whether the dilution is 1 in 10, 1 in 100, or 1 in 1,000, you can actually see it aligns perfectly. You can even, at 1 in 1,000 dilution, you can call this rare variant very accurately. So in this plot, actually, if one dot contains 5 individual dots because there are 5 mutations in this variant. So all these 5 dots are on one single dot because it is that accurate. So it is really nice to see. And on the right-hand side, what you see is the base calling accuracy plot for this variant and 1 in 1,000 dilution. So at 0.1%. Low frequency variant calling. So you can see the accuracy, Q score is very high, it's above Q35. So which means, like, if the Q score is above the frequency of the dilution, that means you can call that variant very accurately. So this is a really nice, interesting feature of Outy sequencing. And also, the other important feature of Outy sequencing is, as I said earlier, so you don't have to do massive depth of sequencing of unnecessary molecules. When you capture the rare molecule that you want to sequence, you can trap that in the pore, and you can read it many times until you hit the right accuracy or the right confidence levels. So this is really the small needle in a bigger haystack. So it's a really nice application of Outy sequencing. So we can also do this, apply this to modifications as well. So in this particular example, we are calling 5MC using Outy sequencing. And as you can see, when you increase the number of rereads, the Q score, the Q accuracy improves significantly. With 10 rereads, it hits about Q25 accuracy, and we can call 5MC with 99.68 accuracy. So this is really high. And on the right-hand side, in the IGV plot, as you can see, the blue is unmodified, red is modified. So most of the strands, you can detect the 5MC modification very accurately. So this is a really nice way to improve the accuracy of modification calling even further. So direct RNA. So direct RNA is actually one of the key and nicest features of nanopore sequencing, because only nanopore can do direct RNA without converting the RNA into cDNA. For a long time, we haven't really, I think for about 5 years or so, we didn't really work on direct RNA because we were working very hard to improve DNA sequencing. But in the last 6 months or so, we have worked on direct RNA to improve the system. A lot of people were asking us whether there are any improvements coming. So I hope this is a really nice message for our RNA community. So this is where we are currently at with direct RNA offering. So our speed is at about 70 bases per second, and accuracy is between 89, 93, depending on whether you are using yeast or human DNA. So It's a really quick library preparation, 30 to 120 minutes. Modified bases are distinguishable, and we are using RNA-specific motor, and because it's direct RNA, so there is no reverse transcription bias. So now we have improved our motor protein and our nanopore as well for direct RNA-specific applications. So in the motor protein, we have improved the speed almost twice. So as I said previously, it was around 70 bases per second. And with the new motor, we are now hitting a speed of about 130 bases per second. What that did was it improved the output significantly as well. So on the right-hand plot, you can see the output of the old chemistry versus new chemistry. The gray is old chemistry, and the blue is new chemistry. In old chemistry, we usually recommend use 500 nanogram input, and with that, you are getting about, this is a PromethION flow cell, you are getting about 9 million reads. With the new chemistry, if you use 500 nanogram input, you are getting about 22 million reads, so that's about a 3 times increase to the output, which is really nice. And the other nice feature is, like, if you have a low amount of input material, you can reduce the input to 50 nanogram, and you will still get the similar output that you were getting with your previous chemistry. So which means we have improved not only the speed, output, but also the sensitivity of the system. So we also improved the base caller of RNA sequencing. We kind of used a larger neural network models and with very kind of diverse training sets, and that improved the accuracy significantly. Accuracy is now, whether you are using yeast or human, accuracy is around 96% compared to 89 to 92 in previous chemistry. So together, so these combined improvements to the nanopore, enzyme, conditions, and model training yield significant improvements to the performance. So just to summarize, for the RNA part, accuracy is now at 96%, whether you are using human or yeast RNA. Output is improved by 3 times, speed increased by 2 times, and sensitivity improved by about 10 times. So this is a big package for RNA sequencing, and we hope that the community will like these updates. So, redefining liquid biopsy. This is new. This is our way of liquid biopsy. So we are a company that we keep talking about sequencing anything, anywhere, by anyone. So to do sequencing anywhere, so we have the right platforms. It's portable. You don't have to do sequencing in the lab. You can take it out to the field, but still you need to do a sample prep stage, which requires some equipment or some sort of lab. So what if we take the sample prep out completely and people can add DNA directly into the flow cell? So this is our way of defining liquid biopsy. So a team in R&D working very hard over the last year or so to develop a method that will take sample prep out of sequencing. So you can add DNA directly into the flow cell. So to do that, we need to change chemistry as well. So in this particular example, what we are showing is a new chemistry method that we are using in these liquid biopsy flow cells. So this is what we call the Nanopore. In this Nanopore, enzyme or the motor protein is actually localized on the pore. And you can then add DNA directly, untreated, without ligations, without adding adapters. And the DNA binds to the motor protein, and it will feed into the pore. It will sequence. When when the DNA strand finish sequencing, pass through the pore, and the next strand will come and captured by the motor. So we have done the proof of concept of this, just the Nanopore itself in normal flow cells. So you can see that we get nice squiggles. So this is actually really interesting because, as I said, you don't need the adapter, and DNA directly can be added to the flow cell. And then to take it to the next level, we need a new, different flow cell design. So this is a prototype device to enable sample-free sequencing, sample prep-free sequencing. So in this particular prototype, you have a receptacle that you can open. And in this receptacle, so there's a small chamber, like you do in COVID testing. You can take a swab, and then you can take any sample, whether it is blood or saliva or anything, and then you can put that swab into this receptacle, and then you can break the swab and then close the lid, and then you can start doing sequencing. So that's the idea of this device. So we are developing this. This is still in very early stage. So we have, so in this device also, underneath this layer of the flow cell, there is a separate semi-permeable layer separating the sample input from the sequencing chamber. So as you can see, the receptacle is the top half of the flow cell. And underneath that, there is a sequencing chamber. And in between those two, there is a semi-permeable layer separating. So the idea of the semi-permeable layer is to ensure that all the other stuff that we don't want to be in the sequencing chamber, so to prevent migrating that. So we can apply, so this receptacle has an electrode, and then we apply potential. Negatively charged molecules will pass through this semi-permeable layer into the sequencing chamber, and then it can start sequencing. So this is, again, as I said, very early stage in development, but we have done the proof of concept. If you add DNA into this receptacle and let it pass through the semi-permeable layer, and it will be captured by the enzyme underneath, and then you will get this sequencing squiggle. So this is actually real data that we got like very recently, and enzyme DNA signal after cross-chamber electrophoresis. This is not where, still, there's lot of work to do in this area, especially to get the sample from swab to go into the sequencing chamber, but it's really promising, and this is where we want to be in the future. So it is sample prep-free DNA sequencing. So with that, this is towards the coming to the end of our technical update. So Rosemary talked about what we are offering now. So we have one platform, read any length from short to ultra long, many applications, and Q20 plus simplex accuracy, Q30 plus stereo duplex, push button workflows, and we are the most comprehensive technology for variant detection and base modification. Then Stu talked about what we are offering next in the immediate future. So main update is the R10.4.1 and Kit 14 full release, and Q20 plus base calling keeps up on PromethION, and he talked about read until with adaptive sampling. 5HMC calling integrated in MinION, high duplex rate flow cells, and Mk1D iPad accessory for next generation of portable sequencing. So in this section, I talked about what coming in the future, higher output DNA sequencing chemistry with high-speed enzymes, new RNA chemistry with improved accuracy and output. So Outy sequencing, which is quite important with 0.1% rare variant calling with methylation, and possibly lab-free liquid biopsy as well. So that is the end of our technical update. So if you want to know more and where we will be in 6 months' time, please do come to London Calling, which will be in London, obviously, from 17th to 19th May, and it will be a hybrid event as well. And thank you very much for your time, for everyone joining us in New York and everyone joining us online.